Hello, Algebra 2. This will be a video of me going over the entire Unit 6 test review. This is mostly for anyone who either failed the test and needs to retake it and would like to catch up on any problems that maybe you didn't understand properly, or maybe you haven't taken the test yet and you need a chance to go over the review and at least see some problems worked out without having to come into tutoring. Okay. To begin with, on the front page, this is a very important page because it's going over not really the fact of these unique functions, but more just the general idea of how do you visualize functions in general when you're transforming them left, right, up, down, or stretch or compress, and what should you keep in mind when you do transform them. So to begin with, the first process that you should look at is what is the parent function of the thing we're looking at. So these are two different kinds of functions, and you notice their defining parts are not the parentheses, not the x, not the g or f of x. It's the thing that is being changed, in this case a cube, or sometimes a square, or sometimes a square root. In this case, this is a cubic function signified by something cubed. Its parent function is x cubed, y equals x cubed. And it's good to visualize what the parent function would look like before we start transforming it or moving it at all. So the parent function of x cubed, the cubic, and it's important to know that this name is cubic, the cubic function. Well, we find it by plugging in some values into something cubed. So let's say we had some x values. The most important x value that you should look at is 0 in the cubic. Actually, all parent functions you should look at 0. So 0 cubed is 0. 1 cubed, 1 times 1 times 1 is 1. 2 cubed, 2 times 2 times 2 is 8. The interesting thing about cubic functions is you guys are so used to square root functions or even functions like the quadratic that aren't necessarily allowed to behave naturally in a negative way. But with cubics, because they're odd powers, when I plug in -1 times -1 times -1 will give us -1. And same with -2. -2 times -2 times -2 should give us -8. So this function absolutely exists in the negative direction, both in the domain, so in the x value, and in the range, in the y values. So we have the parent function. I'll do this in blue. 0, 0, 1, 1, -1, -1, 2, 8, 1, 2, about there, and -2, -8. And then so on and so forth. So 3 would put us at 27, and 4 would put us at 64, but that doesn't fit on this graph. This is popularly remembered as the Elvis function, because this looks like some kind of stick man raising his arms like Elvis and going down like the king himself. But in essence, what have we done to this parent function, this cubic x cubed function? We look at the parts, and all the same parts apply to any transformations. You have some a value at the front of a function. You have some h value on the inside of the function, and some k value on the outside. And all their parts do essentially the same thing. In this case, it's a cubic. So we're taking the cubic function, and we're moving it right with h, right and left, up and down with k, and then our vertical stretch and compression. Hold on, I know how to spell stretch, I promise. I don't promise, actually. Vertical stretch and or compression. And all the parts are the same. In this case, notice there is no a value in the front, which means we assume that that a value is 1. So there was no vertical stretch, there was no vertical compression, and this graph is not flipped or reflected, it is facing upright. It is, however, inside's opposite, so -5 on the inside tells me I'm moving right 5, and k is going up 2. So why is it so important to know 0, 0? I mentioned 0, 0 is the most important point to plug into any function, is because this is the point you should move first. Why? Because if for whatever reason this graph was stretched, if I multiplied it by any number whatsoever, 0, 0 doesn't change. Multiply 2 by 0, it's still 0. The only thing that 0, 0 really represents is the center of your function, and have you moved the whole thing right, left, or up or down. So in this case, our origin, our center of this cubic function, has been moved right 3, 1, 2, 3, up 2. Now, this point is so important that on quadratics it's called the vertex. In all functions, I guess you could call it its center or its origin. But on cubics specifically, on anything with a cubic or odd index, odd power, we call this the inflection point. So if I told you this cubic has an inflection point at 3, positive 5, then you know for a fact you moved right 3, up 5. Because that is the center. The inflection is where it's centered. Inflection point. Okay, so then we look at this, and as we mentioned, there is no a value. It's 1, so it was not stretched, not compressed. This thing is the exact same shape and the exact same size, so we take the usual points. The 0, 0, the 1, 1, the 2, 8, the negative 1, negative 1, negative 2, negative 8, and just plot them around this brand new origin. So pretending that this inflection point is the origin, over 1, up 1, left 1, down 1, and to the right from this new origin, 2, and then up 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then from right 2 from this new origin, 1, 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, not too bad when you have not stretched or compressed your function. You just move it some values. So this would be step 1, move its center, move its inflection. Step 2, of course, is check the function if it has any stretch or compression, and see if it's vertical or see if it's horizontal. So I've mentioned A, H, and K, and those are the only ones I really want to work with in this class, because you really don't want to work with horizontal compression or stretch, just vertical only. So, brand new parent function. It's no longer a cubic. We call this the cube root function as a parent function. So let's look at some parts of where this cube root function would look like. Remember, cube roots are asking a very different question than a cubic, which is, if I plug in a value underneath this radical, this cube root, the question it's asking, like let's say I plug in 0, the question it's asking is, the cube root of 0 is asking, something times itself 3 times equals 0. What is that something? It happens to be 0. And then moving on, something times itself 3 times equals 1. That's easy. 1 times 1 times 1 is 1. And same with negative 1. What multiplied by itself 3 times is negative 1? We've already seen that. It's negative 1 times negative 1 times negative 1. So the answer to this must be negative 1. Now, I don't know the cube root of 2, not off the top of my head. It's probably some irrational decimal. Actually, it is an irrational decimal. The question it's asking is something times itself 3 times equals 2. And working only with integers, or rationals in general, we can't come up with that number. Instead, skip a few paces. Go to the first perfect cube you can think of after 1. And we just spotted it. The first perfect cube I can think of is 8. The cube root of 8 is asking the question, something times itself 3 times equals 8. And the answer to that question is 2. So the cube root of 8 is 2. The cube root of negative 8, similarly, is negative 2. Now notice, what's the relationship that a cubic and a cube root function have together? Their x and their y values are flipped. Now, you can't flip negative 1, or 0, 0, but we can definitely flip negative 2, negative 8, and make it negative 8, negative 2. And 2, 8 turns into A2. So we're going to go from this Elvis vertical-looking function where Elvis is standing upright, and he's going to be on his side. So the inflection point, the most important point, is the same. 0, 0 can't really change. Can't flip-flop 0, 0. And neither can we flip-flop -1, -1, or 1, 1. But I can rearrange 2, 8 and make it 8, 2. So we're going to go from the origin, right 8, up 2. And from the origin, left 8, down 2. And now, if you notice the relationship, it's on its side. In fact, these two functions, the cubic and the cube root, are reflections across y equals x, the diagonal, which makes these two functions, their x and the y are the flips, flip-flopped, switched, makes them inverses of each other. These are inverse functions. Okay, besides that, the cube root, what have we done to it? We look at the a value up front, we look at the h value on the inside, and the k value on the outside. Well, in this case, it's a cubic function. Or sorry, not cubic, cube root function. And actually, it's a very distinct difference. If I tell you it's a cubic function, you know it has something cubed. If I tell you it's a cube root function, it must have this radical of the cube root. So we take the cube root function, and we're going to move it plus 2. So really we went left 2. Plus 4 on the outside is obvious, up 4. And our a value in front, multiplied out front, is a vertical stretch. Why stretch? Because it's 2. Not the negative, just the 2. So, vertical stretch of 2. What does the negative do? Its own transformation, all by itself, a reflection across the x-axis. Which means we flip the function from top to bottom. So, always begin step 1, move its inflection point, move its center. So we're going to start with left 2, up 4. It's brand new center from 0, 0. It's going to go left 2, 1, 2, up 4. 1, 2, 3, 4. And then you ask the question, did we stretch or compress it before we draw the usual points? So imagine if I drew the usual points at this new center, I'd have 1, 1, -1, -1, and 2 from this origin, or sorry, 8 from this origin, 1, 2, 3, 4, 5, 6, 7, 8, up 2. And left from this origin, 8, 1, 2, 3, 4, 5, 6, 7, 8, down 2. So this is what the function would look like if it was not stretched and it was not flipped. So what does it mean to vertically stretch something? The word vertical refers to y values. Vertical is talking about the y values of the function. Now, how are we going to vertically stretch it by 2? Take every y value, multiply it by 2. So what does that mean? Look at all these y values. 0, 0 can't change, which is why we move it first. 0 times 2 is still 0. But 1 times 2. Now we're going to go right 1 up 2. But remember, we're reflecting it as well, so we might as well get that out of the way. We're going to multiply it by -2. So right 1, down 2. Right 8, down 4, because -2 times +2 will give us a -4. And then on the other hand, go left 1, times -1 times -2 would have us going up 2, and -8 times -2, sorry, -2 times -2 would have us go left 8, up 4. So we're flipping it and stretching all of these y values by a factor of 2. So 1 becomes 2, and then flipped. 2 becomes 4, and then flipped. So let's see. Right 1, down 2 would have us go right 1, and instead of go up 1, right 1, down 2. Put us right here. And then right 8, down 4. 1, 2, 3, 4. And then everything on the other side. Left 1, up 2. Left 8, up 4. 1, 2, 3, 4. So that's the process. Move its inflection point first. Step 1, move its inflection point. Then stretch and compress it, and I guess reflect it at the same time. Take every y value. Not too bad. Okay. Their domains and ranges. If you notice, every single x value that I was allowed to plug in, I could plug in 3, 4, 5, 6, 7, all the way to infinity, positive infinity. And in the negative direction, I'm allowed to plug in any negative x value I want. So we would say its domain is all real numbers. And same with its range. If you plug in every positive and negative x value, out comes every positive and negative y value. So its range is also real numbers. Now remember, the cube root function is the inverse of the cubic. So you take the x, take the y, flip them, take the domain, which is x, and take the range, which is y, flip them. But what happens when you flip all real numbers and all real numbers? It stays the same. So these are our cubic and our cube root functions. And how to graph their transformations. Start with its inflection point, then stretch it and compress it. And in my class, we only stretch and compress the y values, vertical stretch only. Okay, number 3. Remember how I said I only want to work with vertical stretch and compression, and we don't want to work with horizontal? On this problem, we're going to explain why. I'll give the short version first and the long version after, so that you could skip ahead if you'd like to. The short version is this 8 is a horizontal stretch and or compression, and it has affected our left and right movement. Because if you look at this graph, I promise you we did not go right 16. In fact, I'll show you. We have 2 times the cube root of 8x minus 16 plus 1, the red graph, and the parent function, the cube root of x. And if you notice, the parent function is centered at 0, 0. And remember, it looks like we're going right 16 in the function. But if you look at its new center, we actually went right 2, up 1. Up 1 didn't change. We definitely went up 1. But we did not go right 16. We went right 2. And the reason why is because this function has been displayed to us in a misleading fashion. In that, when you have an a value out front, that 2 is definitely a. That makes sense. And this is a cubic function, I suppose. But it doesn't need to be that long. But this value on the inside, this 8 being multiplied by this x, is not a vertical stretch or compression or anything. It's not even a reflection across the x-axis. This controls horizontal stretch and compression. And it's not written correctly, because if it was, it would be a b value parentheses our x minus h value on the inside of a parentheses. So right now, this 8 needs to be factored out, and we did not go right 16. And plus 1 on the outside, plus k on the outside. That doesn't change. Factor out the 8, and we're left with x minus 2. We really went right 2, and now this is written correctly. So the short version of this is that if you write 2 as a vertical stretch, the problem itself is saying describe the relationship between this, and this is actually a typo. You could say that these are inverses of each other, but that's too much work. Let's just say they're both cube root functions, not cubics. Describe the relationship between these functions is a SAT style way of just asking what are the transformations happening between the parent function and this brand new function we created. So if you wrote this in totality as a vertical stretch of 2, a horizontal. Now, what do you guys think? It's an 8. It's bigger than 1. Horizontal stretch or compression? It's a horizontal compression of 8. So, notice, vertical stretch of 2, because 2 is bigger than 1. Horizontal compression of 8, because 8 is bigger than 1. They're flip-flopped. That's horrible to remember. That's one of the reasons we don't like using horizontal compression. And right 2. If you said right 16, you're flat out wrong. This graph did not go right 16. It's a horizontal translation of 2. And up 1. Up 1's correct. You can't really break that one. But right 2. If you said all 4 of these transformations, you would technically be correct, and I would give you full credit. It's not a great way to go about it, because in future classes, like pre-calculus or calculus, no one uses horizontal compression. You should factor it out, and you should get it out of this function, because it's a waste of time vertically stretching this function and horizontally compressing it at the same time. Long story short, we're going to take this vertical stretch of 2 and this horizontal compression of 8 and combine them into 1 using a clever rule that says both exponents and radicals, because they are the same, if you have the cube root of 2 things multiplied, or the square root, any radical of 2 things multiplied, then the cube root of a times b can be split up into the cube root of a times the cube root of b. We know this fact to be true because we've seen it with exponents. 2 things squared is the same thing as 2 separate things squared. And radicals are just exponents. We've learned that in this unit. But, essentially, by factoring out our b value, our horizontal compression, now we have something times something. I can write this as 2 separate cube roots. The cube root of 8 times the cube root of x minus 2 plus 1. Now here's the neat thing we've accomplished. That 8 is no longer a horizontal compression. Essentially what you've created is one massive a value at the front of this function, with x minus h on the inside and plus k on the outside. Our entire vertical stretch is made out of 2 times the cube root of 8. Luckily, and we've designed this on purpose, the cube root of 8 is just 2. So our a value is just 2 times 2, or 4. You've taken a horizontal compression and a vertical stretch, combined them into one, and just made it a vertical stretch of 4. And that is lovely. That's really all we want to mess with, and I'd much prefer you guys to do that. Essentially, this is all you need to know for this question. If you want to hear the long story, stick around. If not, move on to the next question. Long story. Okay. We said this was a vertical stretch of 2 and a horizontal compression of 8. And I said we don't like horizontal compression. Turn it into 2 separate radicals and then make one massive a value out front. Why? One, it's easier in general to have less compressions and stretches, but the biggest reason is later on in other classes, you don't want to do horizontal and vertical stretch at the same time. Mostly horizontal. Vertical means y. Take every y value and multiply it by whatever the stretch or compression is. In this case, it's 2. And that's pretty straightforward. Take every y value and multiply it by 2. It's a vertical stretch of 2. That makes sense. But for a horizontal compression of 8, horizontal means x. Take every x value and multiply it by... You guessed it. No, you didn't guess it. It's a horizontal compression of 8. You multiply it by 1 over 8. Or divide every x value by 8, which makes no sense in calling this a horizontal compression of 8. We should be calling it a horizontal compression of 1 over 8, which some textbooks do, a lot don't. So why do I not want to see both of these compressions and stretches happening at the same time? Because if you were going to graph this and understand what was happening to the x and y values, you would take every parent function x and y value you saw and multiply every x by 1 over 8 and every y by 2 at the same time, and that's garbage. Don't do that. So, we get rid of horizontal compression in its entirety, and strictly only work with something multiplied in front of the function. Makes your life easier, I promise. Okay, last question on this page. We're going to be looking at a cubic function. Cubic, how can you tell it's a cubic? I.e. x cubed. Because it looks like our Elvis-looking function, and it's standing upright. If it was on its side, like so, I would say cube root, but this is a cubic. Write the equation for the function graphed. Now there's 2 ways to go about this. 1, you need to know its parent function. We had to know just from the general shape that this is a cubic function, which means we're going to be attaching parts to something cubed, and it's very, very important that we know it's a cubic and not a cube root. So, we need an a value out front. maybe an h value on the inside, moving it left and right, and a k value on the outside, moving us up and down. First things first, where is its center? Just like graphing this function, moving its inflection point first, we shouldn't see its inflection point from the graph. Or if we're given the inflection point, we know its center, i.e. we know h and k. So, based on this looking graph, the center is usually at 0, 0, and it looks like the start of where the curve happens. Where does that exist now? 2, 1. The center of our graph is at 2, 1, which means h is 2, k is 1. We moved right 2, up 1. That's not that hard. Step 2. How do we figure out this a value? Did we stretch or compress? Now, if you have a graph, there's one way to go about it, which is from the center, is it stretched or compressed based on where should the points usually be? Where should our points usually be? In other words, normally with a cubic function, something cubed, we have 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. Let's just check. From this 0, 0, do we have 1, 1? No, we don't. So right 1, how far up did we actually go? Up 3. And then we make an educated guess. How did I get from 1 to 3? We probably multiplied this y value by 3. In other words, our a value is a vertical stretch of 3. And we check it on the other side just in case. So left 1 down 1 is left 1 down 3. We multiplied it by 3. Definitely multiplied by 3. So we could, right off the bat, from the graph say a is 3. Other way, what if they don't give me the graph, and all they tell me is that I have an inflection point, and my graph crosses at one other point? Well, they've given us a couple of extras. We got 3, 4, and we got 1, negative 2. Let's say we pick 3, 4. Let's say the inflection point's at 2, 1, and it crosses at 3, 4. That's all I need to know to fill out what a is, even without a graph, because this is a function where y equals stuff. Well, I have h and k. I have a brand new x and y. Solve for everything except a. So plug in a is 4. Plug in x is 3. And fill in all the other parts. And we have this a value out front that we are going to solve for. My recommendation, stick with PEMDAS. Parentheses, the inside of the parentheses. 3 minus 2 is 1. Next, PE, exponent. 1 cubed is 1. Now, I wrote this kind of funny with a times 1. When normally we would write 1a. But I want to make it very clear. This one and this one cannot add because this one is being multiplied by a. And in the order of PEMDAS, we cannot add or subtract until we've done multiply. And we can't multiply a times 1 except by calling it a. So do not call this a plus 2. You cannot add those ones. But we can multiply this one that's written right next to the a. Because all along, this a is multiplied out front. Can't forget that. Finally, add or subtract to the other side, and we have a equals 3, minus 1 for both sides. So if you don't have a graph, there is a process. If you have an inflection point, your center, and one other point, you're golden. That's all you need to do to construct a function in its entirety. It's a, it's h, and it's k. Okay, I'm going to kind of blaze through this page because it's relatively straightforward. The only thing you need to notice about this page is everything on it has to do with the square root function. So before we touch anything else, let's look at the square root's parent function, which is y equals the square root of x. A couple things, plug in some x and y values, plug in 0, 0, square root of 0, 0. Square root of 1 is 1. Square root of 2 is an irrational number, so I don't feel like it's that useful to plot. But I do know another perfect square, like the square root of 4. The square root of 4 is 2, and the square root of 9 is 3. Plug in all your perfect squares, and you will find the points that are nice and pretty to plot. So the next perfect square after 9 16. Square root of 16 is 4. And that's more than enough. I probably can't even fit the 16 4. No, I definitely can't. But 0, 0, 1, 1, 4, 2, 9, 3, plenty of points. So what do we call this 0, 0 point? It doesn't really have a name. If this was its inverse, if this was an x squared function, 0, 0 would be its vertex, but it's hard to call it the vertex when it's only half of a parabola and not even in a way that makes sense. So I guess you could still call it its vertex, but I don't know if that's semantically true. Anyways, plug in 0, 0, 1, 1, 4, 2, 9, 3. Let's see. Does this graph go to 9? 4, 5, 6, 7, 8. No, it doesn't. Nah, I don't care. 3 points is enough. This is what its parent function would look like. And just like usual, what have we done to it? We've moved it left 1. Because that's our h value on the inside. A, h, and k. And because we were a plus 1 on the inside, we went left 1. And because there's no horizontal stretch or compression, all we really got to do is move the vertex, the origin, left 1. And then plot every point that we are supposed to. So from the origin, we're supposed to have 1, 1. We're supposed to have 4, 2, so 1, 2, 3, 4, up 2. I don't know if these intersect. They probably shouldn't. And that's good enough. Something like that. And then, same with this graph. We have a reflection across the x-axis and right 4. So our origin, which is normally at 0, 0, should go right 4. 1, 2, 3, 4. And because it's a reflection, instead of going 1, 1, let's go to right 1, down 1. And right 4, 1, 2, 3, 4, down 2. That's enough points. And then all the transformations under the sun. We have an a value, an h value, and a k value. Move its origin first. Right 2, up 3. So 1, 2, 1, 2, 3. That's our brand new origin. Pretend that is the origin. Its vertex. And instead of going right 1, up 1, right 4, up 2, we're going to take this a value, a vertical stretch of 4, vertical meaning y, take every y value and multiply by 4. So instead of going 1, 1, we're going to go 1, 1 times 4. And 4, 2, 4, 2 times 4. So that should look like right 1, up 1, 2, 3, 4. Right 4, 1, 2, 3, 4, up 8. 1, 2, 3, 4, 5, 6, 7, 8. Nice. And their domains and ranges. Well, the parent function of y equals square root of x. Notice I didn't plug in a negative 1. That's an inherent fact of the square root function, is that if we're in the real number system, we can't actually plug in negative numbers underneath the radical. The radicand, the thing underneath, cannot be negative. And because of that, y will also never be negative. So the only thing you really need to look at are its h and its k values, which are this function moved left 1. Its domain now starts at 1. Is everything greater than or equal to negative 1? Its range hasn't changed. You haven't raised it up or down, so it's still everything greater than or equal to 0. Domain? On this one, we went right 4. So x is everything greater than or equal to 4, positive 4. But you flipped it. So now all our y values are going in the negative direction. It's every y value less than or equal to 0. And this one, all 3. You're going to notice the 2 and the 3 matter. Right 2, up 3 means our domain now starts at 2. And our range begins at 3 and goes up. But notice 4 doesn't actually matter. We still start at 2 and we still start at 3. 4 just determines how quickly, how fast are we going to increase, not where we start. Okay, I skipped some of the square root problems and we're jumping straight to this page. First, it says solve the following radical equations. It's important to see that they're radical, square root, and remember the 1/3 power we know from the rational exponent rule is just the cube root of whatever that 1/3 power was attached to. So yes, this 1/3 power is in fact a radical equation. Parentheses, check for all extraneous solutions if necessary. A very, very important fact, because some of these problems don't have a solution, or they might have two solutions and one of them is false or extraneous. Now, let's skip ahead to the other page, because this graphic is very helpful. Notice we have two different types of functions, and it even explicitly says we have even functions and odd functions. 1/2, 1/4, 1/6. 1/3, 1/5, 1/7. Given the graphed radical functions above, what kind of radical equations must be checked, and why? And it's a very important distinction between these even and odd functions. Now remember, the 1/2 power is really the square root, and we just don't write the 2. And the 1/4 power is the 4th root. So every single one of these are radical equations. So we're looking at the square root, the 4th root, the 6th root, the cube root, the 5th root, the 7th root. Now, what's the difference between them? Notice every single odd root, every single odd radical exists in the negative direction of their domain and also exists in the negative direction of their range. You're allowed to plug in negative x values and out come negative y values. Whereas every single even radical function, nothing exists in the negative direction in either domain or range. And we know this for one root in particular, the square root, the even root, x to the 1/2 power. If you plug in a negative value underneath, normally we say no solution, but now we know from the quadratic unit, this is an imaginary solution. But if everything we're graphing on is an xy plane in the real number system, we're not allowed to plug in imaginary solutions, so we would say no real solution. And in this unit, that's good enough. So we would say that's extraneous. We can't actually plot that point on a graph. So what kind of radical functions must be checked for extraneous? If you notice the pattern, all the even ones. All the odd ones, A-okay. But all the even roots do not exist in the negative value because of this reason. So the fact that we can't plug in -1 underneath this square root, same deal for the 4th root, the 6th root, the 8th root, can't plug in -1, any negative value. And out, you cannot also get out a negative value. So can't have a negative underneath, not in the radicand, and the square root all by itself cannot equal a negative. So this is the domain, can't break the domain, and can't break its range. Okay, back to this page. Why does that matter? I could right off the bat tell you which of these problems you actually have to check and which of them you don't. 5 square root, 7 square root, 8 square root, 9 square root, 10 square root, all of these have to be checked. So if I use asterisk, must check, then you have to check 5 because it's even, 7 because it's a square root, it's even, 8, 9, 10, and 13 because this is the 3/2 power. And if you guys recall, power on top, flower, power on top, roots are always underground. This is a square root. It's even, must be checked. Now, the interesting one on this page is number 12. And let's look at the others. We have the cube root and odd root. The cube root and odd root. Clearly odd, they don't have to be checked. So much so that if you're on an SAT or a test and the cube root function has an answer choice that says no solution, right off the bat, cross it out, because that's not possible. The cubic, the odd roots exist everywhere. You can't break this function. But 12, it's the cube root, right? Shouldn't break. The issue is this power that's squared. This doesn't break in the usual ways that a square root does, because it's not a radical. You guys know what x squared looks like, something squared. It's a parabola. Can it break? Absolutely. In one case and one case only. We can't have something squared equal a negative value. So let's say I give you a parabola and I ask you, where does it intersect that line? It doesn't. It would have no solution with that line. So as long as this thing does not equal negative, we're A-okay. And in this case, our something squared equals positive 4. This one already can't be broken because not only is it a cube root, its square is positive, and that's A-okay. Okay? So let's go over some examples. The most basic thing to follow is step 1 to any radical problem is isolate the radical. Could be the square root, could be the cube root, could be the fourth root, whatever. Get the root-looking bar, the radical, all by itself. Doesn't matter what is underneath it, the radicand. Just get that entire thing isolated. Now, what do I mean by isolated? Nothing multiplied out front, nothing added or subtracted in the back, and definitely nothing divided. Get rid of these parts, and it's isolated. So start with subtraction, addition and subtraction. Minus 5, minus 5. We have 1/2 square root of x minus 4 equals 3. Cool. Still not isolated. It's something multiplied out front. Get rid of it. The opposite of 1/2 is times 2. So we have the square root of x minus 4 equals 6. Okay. Once you've isolated the radical, bingo. Take this step. If it's even, check it. Does your isolated even radical equal a positive number? If it does, you're good. If it doesn't, problem's broken. So in this case, radical equals positive 6. Check. And it must be checked. Okay? Step 3, I suppose. If it is even or not even, at this point, if you've checked it and it's possible, undo the radical. Now, how did we do that? The opposite of all these radicals are their equivalent powers. The opposite of a square root, the power of 2. The opposite of a cube root, the power of 3. And so on. The opposite of a fourth root, the power of 4. And you guys get the gist. So, the whole point of isolating this radical is that we have to square this entire side of the equation if we're going to undo the square root. That would have looked very ugly if we've done that at the beginning. So we didn't. We isolated the thing we wanted to square. Made our lives easier. Square the entire other side of the equation. In this particular case, it's just 6. Undo the square root. With the square, we're left with x minus 4 equals 36. X equals 40. We must check this solution because the square root can break. Now, what are we checking for? We've already seen that the radical equals a positive number. We don't need to check that. The only thing I need to see is, if I plug in x equals 40, is it going to end up positive in the radicand underneath? So go to the original problem, plug in 40 for x. Hey, what do you know? It's positive underneath. Check. That is a solution. But it is something that must be checked, because x could be negative, x could be positive, x could be 0. It doesn't matter what x is. It just needs to not make this negative once it's plugged in. Okay. All right, number 6. I'm just going to keep going from here and timestamp these. So if you're looking for a particular problem, just skip ahead. Number 6. We saw that the 1/3 power is the cube root. If it helps you to write it as the cube root, do so. At least then you know that this whole parentheses is underneath the cube root attached to this 1/3 power. And the same rules apply. Isolate the radical. In this case, this plus 2 needs to go. We're left with the cube root of 6x minus 5 equals negative 5. In this case, don't need to check. It's not even. Don't have to check that our cube root equals a positive, because cube roots can definitely equal negative. That's A-okay. Nothing wrong with that. Step 3, undo the radical. The opposite of a cube root is the cube, the power of 3. Do it to the entire side of both equations, and now we have 6x minus 5 equals negative 5 times negative 5 times negative 5, or negative 125. Add 5 to the other side, solve for x essentially. Last step is always solve for x. Negative 125 plus 5 is negative 120, divided by 6 will give us x equals negative 60. Now, do we need to check... sorry, why did I say 60? Negative 20. Negative 20. Now, do we need to check this value? No. You can, but it doesn't matter. Because if you plug in negative 20 into the original problem, this cube root does not care if the radicand is negative. So 6 times negative 20 is definitely a negative number. Minus 5, definitely a negative number. But the cube root of negative 125 is A-OK to do. Number 7. This one's an interesting one. Mostly because of how large one side of its equation is and the fact that there's an extra x outside of the radical. Step 1, isolate the radical. Cool, it's isolated. Nothing multiplied out front, nothing added or subtracted. Step 2, check if it's possible. My radical equals x minus 1. I don't know if this is going to equal a positive number yet because I don't know what x is. So I'll have to come back and check this at some point. Square it. But remember I say square the entire side of each side of the equal sign. And here's the issue. If you square the entirety of x minus 1, we have to binomial distribute. We have to FOIL this. This is not x squared plus 1 or x squared minus 1. It is x minus 1 times x minus 1. And we can't forget that fact. So FOILing that out, we should get x squared minus 1x would give us negative 2x plus 1 equals 2x minus 2. All right, this has changed in nature of what the problem is now. It is no longer a radical equation. It is a quadratic equation, and we solve quadratics a multitude of ways. Set it equal to 0, solve using the zero product property. Quadratic formula, completing the square, graphing it, and then looking at its zeros. So many ways. In this case, we designed these so that they're easy enough to factor. So we can use the zero product property by setting everything equal to 0. Add 2, add 2. Subtract 2x, subtract 2x. And now one side of the equation equals 0, we can factor and see if this works out. If not, we can always resort to the quadratic formula. So two numbers that multiply to 3 and add to negative 4. Let's make it 3 and 1. Make them both negative. So we have x minus 3, x minus 1 equals 0. And remember, something times something equals 0. One of these has to equal 0. Why not both? If x minus 3 equals 0, if x minus 1 equals 0, then x equals 3 and x equals 1. And yes, we can have two solutions. It's possible. In this case, let's make sure we didn't break anything. So if we plug in 3 to the original equation, make sure it's not negative underneath. So the square root of 2 times 3 minus 2 would leave us with 6 minus 2 or 4. Bingo. Check. Positive underneath. Equals 3 minus 1, which is positive 2. Check. It equals a positive number. 3 is a solution. Let's check 1. I already see maybe... Nope, actually, nothing will go wrong here. Square root of 2 times 1 minus 2 is 0. A-OK. The square root is 0, 0. We're allowed to equal 0. We just can't equal a negative. Plug in 1 on the left side, or sorry, the right side. 1 minus 1 is also 0. A-OK. X equals 1 is also a solution. Okay, this whole row of 8, 9, and 10 can all kind of be lumped together and isolate the radical, but in slightly different ways because we have choices now. On number 8, we want to isolate the radical. The choice is obvious. Add 1 to both sides, And it's exactly like the number previous, where we have to square both sides, and it turns into a quadratic foiling problem, where x plus 1 times x plus 1 would give us a quadratic. On number 9, we have a choice. Because we have more than one radical, we get to choose which one we isolate. My recommendation, isolate the one that has an uglier mess underneath in the radicand. You could isolate the square root of x, but it's just not as ugly as what would happen if we had to FOIL the square root of x minus 4. So make a choice. Add the square root of x to the other side. And here's what I mean by that. When we're about to square both sides, we have negative 2 plus the square root of x. Again, it's a FOIL problem, but the radical that was kind of uglier, the x minus 4, is now just x minus 4. And we don't have to deal with it by foiling. Whereas negative 2 plus the square root of x, we're going to have to FOIL negative 2 plus the square root of x times negative 2 plus the square root of x. Yeah, I want to flip that around. This looks kind of ugly. Let's just do the square root of x minus 2. Much better. Okay. But now the only thing I have to FOIL is the square root of x. That's so much nicer than foiling the square root of x minus 4. Because first times first should give us square root of x times square root of x is x. Outside and inside is negative 2 square root of x minus 2 square root of x. Or in other words, negative 4 square root of x. And last times last, negative 2 times negative 2 is positive 4. That's not so bad. Whereas foiling x minus 4 is kind of a doozy. So much of a doozy that I'm making you do it on number 10. Which is, it doesn't really matter which one you send over to the other side. Foiling either of these is going to be a little bit of a scary looking thing, but not that bad. So let's just say we send this one over to the other side. One is not easier than the other. So we have the square root of x minus 2 equals 1 minus the square root of x minus 1. Foil the right side here, and we have 1 minus the square root of x minus 1 times 1 minus the square root of x minus 1. That'll give us first times first is 1. Outside and inside should give us the same object, negative 1 square root of x minus 1, or just negative square root of x minus 1. And last times last, negative times negative is positive. Square root of x minus 1 times the square root of x minus 1 is just x minus 1. And luckily, adding this binomial x minus 1 doesn't change the sign, so I could just get rid of those parentheses. Now, the interesting thing is negative 1 square root of x minus 1 minus the square root of x minus 1. Just count how many square root of x minus 1s we have, or negative 2 of them. Okay. And now these two problems have essentially turned to the same kind of problem, which is that we have a brand new radical, all isolated, the square root of x in number 9 and the square root of x minus 1 in number 10. Go back to step 1 of any problem, which is isolate the radical. So on number 9, get the square root of x by itself. Minus x, minus 4, minus 4. And we are left with negative 8 equals negative 4 square root of x. And luckily, our square root is going to equal a positive number if I divide both sides by negative 4. And we have the square root of x equals 2. Isolate it. It equals a positive number. That's A-OK. Check. Square both sides. And we have x equals 4. We should definitely check this answer. Go to the original problem. 4 minus 4 is 0. Good. Square root of 4 is a positive number. Good. We have broken nothing. X equals 4 is an answer. Number 10. Same way. Isolate the square root of x minus 1. Minus 1, minus 1. Plus 1, plus 1. In other words, they cancel. And then minus x, minus x. So we got x's are gone, left with a negative 2 equals negative 2 squared of x minus 1. Divide both sides by negative 2, and I'm left with a positive 1. Square both sides, not too interesting because 1 squared is just 1. And then we have 1 equals x minus 1, add 1 to both sides, x equals 2. And we should check it. Our square root all by itself equaled positive 1. That was a check. I should have mentioned that. But plugging x equals 2, 2 minus 2 is 0, that's good. 2 minus 1 is a positive number, that's good. A-okay. Okay, radical inequalities. They only really have one thing added extra to them that radical equations don't have, which is we're going to solve it like usual, which is isolate the radical, equals 9, square both sides, and we're going to get x plus 5 is still less than or equal to 81, minus 5 to both sides, and we have x is less than or equal to 76. So this is definitely part of the answer. The only other thing we have to check is all along x is less than or equal to 76 is a lot of numbers. There are a lot of numbers that are less than or equal to 76. We need to make sure all of them are okay to plug in here. I'll give you an example. What's a number that I could think of that's less than or equal to 76 that might break this problem? Like maybe negative 7. Negative 7 is definitely less than or equal to 76. But if I plug in negative 7, this problem is broken, because I would have a negative underneath the radicand. So how do I make sure that doesn't happen? Take the radicand, and when I say radicand, it's the object that is underneath your radical. In our case, it's x plus 5. Make sure that is never less than or equal to 0. So make sure it's greater than or equal to 0. Sorry, make sure it's never less than 0. Make sure it's never negative. So we just make sure it's the opposite of negative, greater than or equal to 0. When is this thing okay? When x is greater than or equal to negative 5, minus 5 to both sides. As long as this thing is true, then this thing can also allow to be true. Now, sometimes it's redundant. Like, let's say I state all the values have to be greater than or equal to negative 5. Well, my answer here in the original solving might already include that, and it's not necessary to state it any further. In this case, that's not true, because if I am less than or equal to 76, but I'm greater than or equal to negative 5, that negative 5 definitely matters. So this is a combined answer of x has to be between these two values, otherwise this whole thing breaks. Now what would that look on 16? We really need to only add in one other extra rule that we commonly forget when we're tired and taking a long test, which is when do we flip inequality symbols? When we divide or multiply by a negative. So isolate the radical, plus 2, plus 2. The square root of 8 minus 4x is greater than or equal to 8 plus 2 is 10. Square both sides now that it's isolate. And actually, we should check here. Is my square root allowed to be greater than or equal to 10? Absolutely. As long as it's not less than or equal to a negative number, then we haven't broken anything. So we have 8 minus 4x is greater than or equal to 10 times 10 is 100. Minus 8, minus 8. Negative 4x is greater than or equal to 92. Divide both sides by -4. We've done it. In fact, the second you divide by a negative number, immediately change the inequality symbol before you forget. X is now less than or equal to -23. Okay, we have one fact. Step 2, when is the radicand not negative? When is 8 minus 4x greater than or equal to 0? Let's check. -8, -8. -4x is greater than or equal to -8. Divide both sides by -4. We've done it again. You flip the inequality. X is less than or equal to +2. Now let's check. Is this necessary to state, or is it redundant? One clue to suggest that it might be redundant is our inequalities are facing the same direction. We are less than -23. This for sure has to be a part of the answer. But does it matter to state that we're less than or equal to 2? Well, let's see. Imagine I plug in a value that's less than or equal to -23. Like, let's say I pick x equals, well, equal to, so -23. That satisfies this. Is -23 already less than or equal to 2? Yes, and I didn't even have to say it. Or in other words, if I put this on a number line, and I say, first and foremost, I have to be less than or equal to -23. And then afterwards you tell me I have to be less than or equal to 2, well, that doesn't really matter. I'm already less than or equal to 2. It doesn't matter. We would call it redundant. Or you don't have to state it in the final answer. In fact, this is usually something that will distract you from what the true answer is supposed to be. So the only thing that needs to be stated is x is less than or equal to -23 and nothing else. Okay, number 17. Common style question on the SAT and on my tests. Graph f of x is less than or equal to, is equal to the square root of x plus 1 minus 3. So the same parts apply. We went left 1, down 3, and the graph reflects that. We definitely went left 1, down 3. Works for me. Determine which of the following is a solution for y is strictly greater than. So we have to recall, what does it mean when our inequality is just greater than, not equal to? That means nothing on this actual function is a solution. We can't equal this line. We can't be on this line. We would normally show this with a dotted line. I'll show it in color. We normally show this with a dotted line. If you put any point on that line, it's not a solution because it would be equal to, and we're not allowed to be equal to. So we need to make sure what is bigger, greater than, in other words, above, all these values above. And not on the line, because if it was on the line, we would be equal to. So, which of the following is a solution? I've got -2, 4. That would be left 2, 1, 2, down, no, up 4. Well, clearly not. It's not in the range. And we could clearly see that because we went left 2. And we are only allowed to start at 1, -1. So this is already at, we have 0, 7, 0, 1, 2, 3, 4, 5, 6, 7. Yep, nothing wrong with 0, 7. And let's double check all the others just in case. 1, -3. 1, -3 would put us right here. Not okay. Easy way to see why is, well, it's not in the colored area. And D, 3, -1. 1, 2, 3, -1. I think that actually puts us on this line. Let me see. 3, -1 means we plug in 3. 3 square root of 3 plus 1 is square root of 4, which is 2 minus 3 is -1. Yeah, this is on the line. And we can't be on the line because this is strictly greater than, and we can't equal to. So D can't be an answer because it's on the line. And it's good to notice why that's not okay. Okay, this is the simplifying rational exponents section. To begin with, we need to know how to simplify exponents. I guess I should show you 18 at the top. If 4 to the 6 times y equals 4 cubed, then 4 to this, essentially it's asking, if 4 to the 6th times something is 4 cubed, what does that something have to be? This is definitely aligned with the rest of the page because this has everything to do with exponent rules. The first thing you should notice is that we start with a 4 to the 6th and we end with a 4 to the 3rd power. The base 4 stays, which suggests to me that this something probably has a base of 4. The question is, what's its exponent? Well, 6 and something made 3. Well, what's our exponent rule say? If I have some object to some power times some object to some power, like base times like base, we add their exponents. So 6 plus question mark equals 3. Well, that's got to be negative 3, which means our exponent, our y, our missing thing, must be negative 3. Okay. And if this was free response, I suppose we should write this as 1 over 4 cubed. Yes. The only thing I don't want you to think is the negative exponent tells us we should flip the exponent. No, not true. Negative exponents flip the entire base. So 4 went from the numerator, because this does have a denominator of 1, went from the numerator to the denominator. But it still stays a 3. It doesn't become 1/3. That would be the cube root. So these are 2 acceptable answers and nothing else. Yeah, I guess you could call it 1 over 64, but that's about it. Okay. Moving on to the rest of the page, we have number 19, which is the very basics of if you have base times base, like base times a like base, then we add their exponents. Does not matter what the object is. In this case, it's 4/5 and 6/5. You just need to know x to the something times x to the something. You add the 2 somethings. And in our case, it's 4/5 plus 6/5. But they did not have to have the same denominator. When I say base, I don't mean denominator. I mean the x. The x's are the bases. So 4/5 plus 6/5 is 10/5, which happens to reduce to x squared. Number 20. We don't have 2 bases. It's a power raised to a power, which tells us we should multiply these exponents. So y to the 2/3 times 3/4. We need to just recall how to multiply fractions, which is numerator times numerator, denominator times denominator, which will look like y to the 2 times 3 over 3 times 4. Or y to the 2 times 3 is 6, 3 times 4 is 12. This happens to reduce to y to the 1/2. And we can absolutely leave our answer like that, as long as you know it's power on top, root on bottom. And this could be written as the square root of y to the first power, or just the square root of y. Number 21. Again, add like bases. Or not, multiply like bases, x times x, add their exponents. And yes, we can add 3/8 and 4/3. They do not have to have the same denominator until we realize we have to add them. So x to some exponent times x to another exponent, add the exponents. Like bases, add the exponents. But in this case, 3/8 plus 4/3, they need a common denominator. And 3/8. 3/8. 8 and 3, I would say 24. So that would be x to the 24. And 3/8. 8 times 3 is 24, so 3 times 3 would be 9. 3 times 8 is 24, so 4 times 8 is 32. And 9 plus 32 would give us x to the 41 24ths. And 41 is prime, so I don't think this reduces. Nope, we're done. 22. A like base divided by a like base. Top exponent minus bottom exponent. This fact remains. It just happens to be the exponents is 1/2 and 1/3. So we have top 1/2 minus bottom 1/3. Which, subtracting fractions, we also need a common denominator. So we have x to the 2 and 3 should make 6. Let's see. 2 times 3 is 6. 1 times 3 is 3. 1/2 is 3/6. 3 times 2 is 6. 1 times 2 is 2. So we have 3/6 minus 2/6, which will leave us with x to the 3 minus 2 is 1/6. Perfectly acceptable answer, unless you'd rather call this the 6th root of x. Also perfectly acceptable answer. 23. Okay, we're done with variables, which are relatively obvious. Combine the like bases if you can. Add the exponents, multiply the exponents, subtract the exponents, do whatever you gotta. It's a little more interesting if we don't necessarily have like bases. Then the second rule we should apply, besides combine like bases, is if you see a radical and it happens to have an index, which in this case is 4, can I make that radical as small as possible? So, big radical index. Can I make it some way, somehow, small radical index? Now, how do you do it? How do you go about that? My recommendation is view all of your radicals as rational exponents. So this is 49 to the 1/4 power. Because it's 49 to the first power, the root is 4. Power on top, root on bottom. Why would I write it like this? Because it makes it abundantly clear that I want this 1/4 exponent to reduce some way, somehow, big to small, with some power, some other exponent that maybe I can make 49 written as. In this case, can I write 49 as some number to some power? 7 squared is the first thing that comes to mind. So 49 is 7 squared raised to the 1/4 power. Now, how does a power to a power interact? We multiply. And 2 times 1/4 is 2/4. And we've done it because we wanted to make that 4, that index of our radical, smaller if possible. And because 49 can be written as 7 squared, they interact with each other like a fraction. Something squared, 4th root, interact by reducing. And we're left with 7 to the 1/2 power, or in other words, the square root of 7. So, this is probably the easiest way to come to the smallest thing possible. How do I know 7 to the 1/2, or the square root of 2 is the final, square root of 7. Square root of 7 is the final answer. Because I can't think of writing 7 as another number to some power. 7's prime, that's as good as it gets. This 1/2 is going to be stuck, and that's fine. But this is the easiest route to take logically to me. The other option would be you view this 4th root as what it is. The 4th root of some object is asking the question, something times itself. 4 times equals that object. In our case, it's 49. That number is not rational. In fact, it's very irrational. We have just shown that it's the square root of 7. So if you can clearly see in your head that the square root of 7 times the square root of 7 times the square root of 7 should equal 49, good on you. You understand this perfectly. But that's quite a leap for most folks. So rely on the rational exponents to give you a hint as to what power should you aim for so that they reduce. 2 and 1/4 definitely reduce. I would have aimed for a 2 or a 4 or some even number that would reduce with 1/4. So, final answer, 7 to the 1/2, or the square root of 7. 24. Rule number 2. Combine like base. Big index to small index. Rule number 3. If you have too many radicals, like a square root and a square root, put them together as a single square root. Or in other words, this is the exponent rule. If I have a squared times b squared, if at all possible, I could write this as ab squared. So, square root of 32, square root of 16. Right off the bat, if you wanted to, we could just call this the square root of 32 times 16. Is it super helpful to do that in this case? Not necessarily. Only because 32 and 16 are kind of large, and multiplying them together would probably be a bad idea to try to find their perfect squares. Rather, if we can, try square rooting these and see if it's possible. Square root of 16, absolutely, it's 4. Yay, we've already gotten rid of one of the radicals. Square root of 32, not so much. Something times itself equals 32. And then we ask the question, old school, can we find a perfect square in 32? Yes. It is made up of 4s, and it's made up of 8s, and it's made up of a 16. 2 16s, in fact. The square root of 32 is 2 times 16. Or the square root of 2 times 16. In our case, the 2 stays, but the square root of 16 we've already seen is 4. So we have the square root of 4 times 3 times 4. The square root of 2, nothing we can do about it. 2 does not change in any way, shape. All these prime numbers, like we saw earlier, the square root of 7, square root of 5, these are irrational numbers that cannot reduce any further. So we're stuck with 4 times 3 times 4, or 16 times 3, which is 48, square root of 2. And that's got to be good enough. Okay, normally I guess I should probably do 25 and 26, but 24 jumps immediately to 27 in my head, in the rules order. Combine like bases if possible. Make the index big to small if possible. Combine like radicals, if possible. Combine the square roots, combine the cube roots. But what happens when we hit 27 and we hit rule number 4? Which is if you have more than one root, like let's say you have a cube root and you have a square root, some way, somehow combine those into a single root. Okay. How? View them as exponents. 25 to the 1/3 and 125 to the 1/2. Because then I know a rule that combines exponents. Like base times like base. I can add their exponents. Then the only thing I need to look for in this problem is some way, somehow, can I write 25 and 125 as the same base. Luckily, they are all made out of 5s. 25 is 5 squared. 125 is 5 cubed. And 5 squared is being cube rooted, and 5 cubed is being square rooted. I can absolutely combine their exponents now. 2 and 1/3 make 2/3. 5 times 2 times 1/3 is 2/3. And then 3 halves. I can absolutely add together 2/3 and 3 halves. Finding the common denominator of 6, we have 3 times 2 is 6, 2 times 2 is 4, 2 times 3 is 6. 3 times 3 is 9. 4 6 and 9 6 will give us 5 to the 13 sixths. And technically we're done, but we shouldn't leave the 13 sixths the way it is. That leads itself to rule number 5, which is kind of rule number 2, which is, can we make the big index smaller? This is a root of 6. Can we make it smaller? But it's more of the fact that it's an improper fraction. In that if you have an improper fraction as an exponent, resolve it. Now, how does this look like as a fraction? How many 6's fit in 13? 2 of them. In other words, 12. So this is really 12 sixths times an extra 1 sixth. That makes our 13 sixths. 12 sixths plus 1 sixth. But 12 sixths is 2. So this is 5 squared, or 25. And we're left with 5 to the 1 sixth. And you've resolved it. Or maybe a better way to view this is thinking of this as the 6th root, root on bottom, 6th root of 5 to the 13th power. And the 6th root is asking, how many 6's fit in 13? How many groups of 6 5's? So we have 2 of them. Pull out 12 of these 13 5's, and we're left with 5 squared, or 25. And how many 5's are left on the inside? A single one. Okay. Now we're done with 27. Let's just go back to 25, which is something 22 could have turned into. 22, we took the top minus the bottom. Like base minus divide by like base, we subtract their exponents. It's always top minus bottom. The only reason 22 didn't turn into something like 25 is that the top fraction was bigger than the bottom fraction. 1/2 is larger than 1/3. The issue here is that we are left with 1 over x to the 2/5 in the denominator, whereas in number 22, we are left with x to the 1/6 in the numerator. And that's okay. We can't leave this 2/5 in the denominator because you can't leave radicals in the denominator. Old conventional rule. That's just something we always have to fix. I guess rule number, I think I'm at 6 now. Never leave radicals in denominator. And you just need to recognize now that the 2/5 power is a radical, because the 5 is the root. So how do we undo this? With square roots, it's simple enough. You take the denominator of a square root and multiply by a square root. But this is not a square root, this is a 5th root. The ultimate goal is we want to multiply this fraction by x to some exponent in the numerator and the denominator, so the result is just an x to the 1st power in the denominator. So recall, x times x, we add their exponents. So we want 2/5 plus something to equal 1. Well, 2/5 plus 3/5 will give us 5/5, or 1. So to complete or rationalize the denominator, which is what this is called, we need to complete the fraction so that it becomes a whole number, in this case 5/5, or 1. So we end up with the final answer of x to the 3/5 over x. So if I'm given the 5th root of x squared, multiply top and bottom by the 5th root of x cubed. Why? Because the 5th root of x squared times the 5th root of x cubed is the 5th root of x to the 5th, which is just x. That's the goal. We want to have our denominator just be an x. Okay. Number 26 I'll leave for last, just because it's a bit of a doozy, and it's not that interesting. It's just really long. Number 28. Okay, let's dissect it. The 4th root, too big. Some way, somehow make it smaller. I have a 6 that will interact with this 4. I have a 144 that I bet I could write as some number to some power. So this is really 144 x to the 6th raised to the 1/4 power. And I want this 1/4 to interact with some powers so that it reduces. 4 reduces with even numbers. So 6/4, that's going to be great. 144, maybe try 12 squared. That'll fix things. And leave this x to the 6th as x to the 6th. Distribute the 1/4 and we get 12 to the 2/4 and x to the 6/4 happens to reduce. 2/4 is 1/2. 6/4 is 3/2. We have 12 to the 1/2, x to the 3/2. X to the 3/2, remember, improper fraction, we want to reduce it or simplify it if possible. How many 2's fit in 3? A single one. So we have really x to the 2/2 times x to the 1/2 left over. And that's just x, square root of x. And 12 to the 1/2 power is really the square root of 12. Are there any perfect squares in 12? It happens to contain a 4 in there, so it's 3 times 4. Square root of 12 is square root of 4 is 2. So 2 square roots of 3. Last thing I would want to do is combine these roots. So we have 2 times x times the square root of 3x. Okay. Next step, we've got 29, which is, again, combine all the like bases. Step 1. I got a like base, divide by 2 like bases being multiplied. Let's combine these multiplications. Like base times like base, add the exponents. 1/6 plus 1/2. We're going to need a common denominator of 12. 6 times 2 is 12. 1 times 2 is 2. 2 times 6 is 12. 1 times 6 is 6. So 2/6. 2/12 plus 6/12 gives us 8/12. So we have n to the 8/12 and n to the 1/3. Let's write 1/3 as a 12. So 3 times 4, 1 times 4, so 4/12. And we subtract top minus bottom. 4/12 minus 8/12 is going to give us negative 4/12. Or just know that the larger exponent is in the denominator. We're going to flip this and just end up with 1 over n to the 4/12 in the denominator. Can't leave it like this. So we fix it. 4/12 reduces to 1/3. What is the fraction added to 1/3 that completes it? 1/3 plus 2/3 will make 3/3. And we're left with n to the 2/3 over n as our final answer. 30 won't be on the test. Old school rule of how do you rationalize this denominator? Multiply it by its conjugate, which is 4 minus the square root of 6. Important thing to know, but not on this test, so I won't go over it. 26, however. Lots of like bases. I have a's, a cube root of b to the 4th, square root of a, square root of b cubed. I have a radical in the denominator, which I can't leave. So let's see what I can put together. This is a to the 1st power in the numerator. And the cube root of b to the 4th power is b to the 4/3 over. The square root of a is going to be a to the 1/2. And the square root of b cubed is going to be b to the 3/2. Okay, like base over like base. We subtract top minus bottom. Now let's see what we're going to end up with. 1 minus 1/2 is 1/2. That's great, because now all I have is a to the 1/2 in the numerator. 4/3 minus 3/2. Need a common denominator of 6. 4 is going to become 8. 8/6 minus 2 is going to become 9/6. 3 times 2, 4 times 2, 2 times 3, 3 times 3. 8 minus 9/6. Turns out 3/2 is larger than 4/3. So we're going to end up with a negative value, or we're going to end up with our fractional exponent in the denominator, or 1/6 in the denominator. Can't do that. So we fix it by multiplying top and bottom by some value that completes 1/6. 1/6 plus 5/6. 1 plus 5 is 6/6. And we're left with a to the 1/2, b to the 5/6 over just b. Or if you'd rather see this in radical form, which we probably should because the problem started in radical form, is the square root of a times the 6th root of b to the 5th power over b.